All right, guys, and welcome back. We are going to finish up section 2.3 with this video. I'm just going to hit some highlights here. So I want to look at number, let me share my screen. I want to look at number 115 in the examples here. If I can find it. So 115 says in the following exercises, use a calculator to draw the graph of each piecewise defined function and study the graph to evaluate the given limits. I'm going to show you how to do this on Desmos. That way you can kind of look at it. So let me just close all of this stuff out. I just keep everything apparently. So here's how we are going to write this out. So our function was, let me go back to it. If you want to take a second to write this down, our function is f of x equals x squared as long as x is less than or equal to 3, and x plus 4 as long as x is greater than 3. You can get Desmos to graph this. Now, one of the things I do want to mention, and I think I've said this in a previous video, Desmos does not show holes. So you have to remember that with the x plus 4, there is going to be a hole there. So to type this in on Desmos, and there's a couple different ways to go about it. I'm going to do it this way. So I'm going to let f of x be equal to, then I'm going to do some braces here. X, and then I need a less than or equal to, and I believe there is a key function for that down here. Yep, less than or equal to 3. So please notice with this, which is a little bit different if you're using a TI 83 or 84, we actually put in our intervals before we type in the function that we're looking at. So we're going to say x is less than or equal to 3. I'm going to do a colon here, x squared. And then I'm going to do a comma. Nope, not up there though. I'm going to hit my right arrow key. And then I'm going to do it again. So I'm going to do x is greater than 3. When we're talking about x plus. Nope. X plus 4. Don't know what that is. There we go. And then I'm going to close my brace. All right. So here's what we see, right? We've got this really pretty graph. We do see something weird happening when we have x squared versus the x plus 4. One's part of a parabola, the other is a linear function. So we are asked to find the limit as x approaches 3 from the left and the limit as x approaches 3 from the right. So if I'm approaching 3 from the left, here's going to be 3 right here. So as I approach 3 from the left, I do see that I am headed towards 9. So the limit as x approaches 3 from the left of f of x is going to be 9. And then from the right side, of course, I am approaching, it looks like 7. So that's the two limits. Of course, the limit doesn't actually exist because there's a jump, but if we look at it from the left or right, those will have a limit for them. Again, guys, I don't know if I've mentioned this. This is called a piecewise defined function, meaning you're getting something that's coming to you in pieces defined by particular intervals. So this is a piecewise defined function. Cool. All right, so I just wanted you to be able to see how Desmos works this one. You know, not super complicated. We actually did this idea back in the previous section. All right, so let's go back now. I want to look at number, I believe 119. So 119 does something really interesting. They're giving us a graph for f of x. So this is a graph that's associated with f of x. This is a graph that's associated with g of x. So on number 119, they ask us to do something weird. They ask us to find the limit as x approaches negative 3 from the left of f of x minus 3 g of x. So I'm going to use those rules for limits, and I'm going to say, okay, well, I can split this up, and if I can find the limit as x approaches -3 from the left of f of x, I can subtract from it 3 times, because remember, you've got the constant rule that says you can pull the 3 out. 3 times the limit as x approaches -3 from the left of g of x. So let's come up here and let's find some information here. So I want to figure out what is the limit as x approaches -3 from the left of f of x. So I'm going to go up to this graph here. So I'm approaching -3 from the left. This is my f of x graph, right? So as I'm approaching -3 from the left, it does look like we are going to get a 0 in that spot. So my first value there is going to be a 0. Let's talk about what happens to g of x. So I'm going to switch graphs because I'm looking at g of x. So as I approach g of x from the left as well, right? Everything's from the left with this one. It looks like for -3, I am approaching -2. So I'm going to take that information and I'm going to use it to do number 119. So let me pull up here an annotate menu. So 119, remember, this is the same thing as saying the limit as x approaches -3 from the left of f of x minus, I can pull the 3 out, the limit, and these rules should look familiar, that's from the previous section, 3 from the left of g of x. And so we come up with the values. We said the limit as x approaches -3 from the left of f of x was going to be 0, minus that 3 is just going to come down because that's our constant. And then the limit as x approaches -3 from the left of g of x was a -2. So if I work my math out here, I am going to end up with a +6. So guys, they can ask a bunch of different questions with this. If you'll notice these next couple of examples, they do a bunch of different things with it. It's the same thing. You just have to figure out what your limit is and make sure that you're using the right graph, right? If it's the f of x, use the top graph. If they're talking about g of x, use the bottom graph. All right, cool. So there's one other topic that I want to talk about in this section, and that is something that's really important to calculus. And if you decide to move on with math, maybe math is going to be your major at some point, you may be taking a class called real analysis. If you take a class called real analysis, you're proving calculus, and this theorem becomes very important in that class. So the squeeze theorem, where are you at? So the squeeze theorem says let f of x, g of x, and h of x be defined for all x not equal to a over an open interval containing a. So you've got an a somewhere in there. Did I want to show an example here? Yeah, let me back up. Let me talk about this paragraph here. So the techniques we've developed thus far work very well for algebraic functions, but we're still unable to evaluate limits of very basic trigonometric functions. The next theorem, called the squeeze theorem, proves very useful for establishing basic trigonometric limits. This theorem allows us to calculate limits by squeezing a function with a limit at a point A that is unknown between two functions having a common known limit at A. So that's how this works, guys. G of x is going to be the function that we're given, and we're going to use two different functions to kind of squeeze it in there to where, you know, if that function g of x lies between f of x and h of x, whatever their limit goes to, g of x also has to go to. Okay, so that's what that was saying. So the limit as x approaches a of f of x equals L, which is the limit as h of x approaches, or the limit as x approaches a of h of x, where L is a real number, then the limit as x approaches a of g of x equals L. So in other words, we're squeezing those two functions close to the function that was given to us. The squeeze theorem can be a little hard to think about the two functions you need to find to squeeze your applications here. Typically, I go based upon what's given in the problem. So I'm going to show you how to do number 127. So number 127, they say for the following problems, evaluate the limit using the squeeze theorem. Use a calculator to graph the functions f of x, g of x, and h of x when possible. And so 127, they give us the limit as theta approaches 0, just another way of saying x, of theta squared cosine of 1 over theta. So here's how I'm going to do this. G of theta, not g of x in this case, g of theta is going to be that function that is originally given to us. And then I'm going to kind of use this thing here. So this thing that's out front, that's how I'm going to find my other two functions. So if I go through and work this, let me pull up a whiteboard so we've got it to look at. So I'm going to go ahead, I'm going to label, well, our original statement was the limit as theta approaches 0 of theta squared cosine of 1 over theta. So I need to find something for f of theta. I know what g of theta is. G of theta is going to be theta squared cosine of 1 over theta. And then h of theta, that's something else. And like I said, guys, I'm going to kind of base it on this little piece right here. So for f of theta, that needs to be less than what theta squared cosine of 1 over theta is. So I'm going to make it negative theta squared. Notice I don't really care about the cosine. So, you know, even though this is cosine that I'm using in my g of theta, I'm not going to use cosine in my other two pieces here. So I'm going to let h of theta be theta squared. And so what we can do now, and the reason I want to do these, guys, theta squared and negative theta squared are just parabolas. So we got a parabola that's pointing up, we got a parabola that's pointing down. Very, very easy to figure out what our limit's going to be here. So here, I'm going to find the limit as theta approaches 0 of f of x. And of course, if I plug 0 in for theta, negative 0 squared is going to be 0. So I'm going to do the same thing for h of theta. So I'm going to have the limit as theta approaches 0 of h of x. Again, when I take 0, if I plug it in for theta and squared, I'm going to get 0. So because theta squared cosine of 1 over theta lies between these two functions, and both of these functions are approaching 0 from both sides, that must also mean that g theta, or g of theta, is approaching 0. So the limit to g of theta is going to also be 0. And that's simply by the squeeze theorem. Now, guys, let me explain to you a couple reasons why I couldn't just do the standard direct substitution. If I took this 0 here and tried to plug it in for theta here, we have an undefined statement. So already I've got an issue. So what happens? Let's actually look at this graphically. So let's stop share. I'm going to reshare. Why won't you let me go to my thing? Okay. Zoom is being stubborn. Okay, wouldn't let me touch it with my finger, but it'll let me do it with a mouse. So let's go back to Desmos. I am going to close this out. Let's do F of, now, you know, your thing uses theta. I'm going to use x. It's all the same thing. So I'm going to have f of x was equal to negative x squared. All right. We're going to let g of x, and I'll change colors here in just a second, equal, what was g of x? Oh, I've lost it. Oh, theta squared. Ooh, theta squared cosine of 1 divided by theta, in my case x, because I don't want to try to find a theta. And I'm going to have to go back and fix this because it did something really weird. Let's, okay. Try this again. Cosine of 1 divided by theta. And then finally, let's make h of x be equal to theta squared, or x squared. Okay. So here's what happens. I'm going to see if we can zoom in. We have something really, really weird happening with g of x. So as g of x approaches 0, it just keeps oscillating. And if I could zoom in even more, do you see how all those oscillations are coming out as I get closer and closer to 0? So it's just continuously oscillating, oscillating, oscillating. That's why we need to have f of x and h of x to kind of figure out what it's going to oscillate to. Because, you know, even Desmos here, as I scrolling closer and closer to 0, I'm not getting anything from this. But because I've used f of x and h of x, sorry, I know that I'm approaching 0 just because of these two things approaching 0. And guys, again, I took the easy way out. I used this negative theta squared and theta squared, or, you know, on Desmos x squared, to make it look nice and be really simple and easy. You're just trying to find two functions that's going to squeeze that thing in there, and those two functions did that beautifully. All right, so that's the squeeze theorem. Honestly, don't know if it'll ever come back up in this class. It may do it. I don't know. I've only worked through about chapter 3 of this book, so we'll see. Sometimes it does, sometimes it doesn't. One more problem, and then we are done with this section. So I am going to go back to section 2.3. I want to do a real life problem here, so I want to look at number 129. So in physics, the magnitude of an electric field generated by a point charge at a distance r in a vacuum is governed by this particular law here, where E represents the magnitude of the electric field, Q is the charge of the particle, R is the distance between the particle, and then that constant there is going to be that. So they ask us to use a graphing calculator to graph E of R, given that the charge of the particle is Q equals 10 to the negative 10. Now that's something that you can very easily do on Desmos. So I think I'm going to have to write all this stuff down because I don't have it wrote down on my piece of paper and I'll never keep track of it. Let's see. Let's go back to Desmos here. Get rid of our squeeze theorem here. So we had E of, come on, E of R equals, and then they told us a bunch of stuff to plug in here. So they did tell us that Q is the charge of the particle, and they give us the charge of the particle to be 10 raised to the negative 10th. So we're going to have 10 raised to the negative 10th. And all of that's going to be divided by a bunch of stuff here that I got to try to get typed in correctly. 4. We need a pi here. Do we have a pi symbol? Oh, my menu's in the way again. Pi. Now, why did you come off the bottom there? I don't want you off the bottom. So 4 pi. E of 0. Where are you at? E of 0. E represents the magnitude, Q is the charge of particle, R is the distance between the particle. Oh, 1 over 4 pi e to the 0 is that constant there. So I actually don't need the 4 pi e to the 0. That's going to be replaced with this lovely, beautiful constant, this column. I think that's how you say it, constant. Then we got r squared. Okay, so let me back up a little bit. So instead of having all of this big division problem the way I had it originally, I'm going to go in here and I'm going to say, oh, we're going to use this big number here. So I'm going to have 8.988 times 10 to the 9th. Is that the whole number? Yep. And then all of that is going to be divided by r. There we go. Okay. So let me back out here. Where's my graph at? There's my graph. Okay, so I want to figure out, I'm asked to evaluate the limit as r approaches 0 from the right. So the limit as r approaches 0 from the right. Well, if I'm approaching 0 from the left, woo, my limit is going to be positive infinity. So my limit's going to be positive infinity. So let me flip back over here. So the limit to this thing is going to be positive infinity. Guys, please pay particular attention. This was the formula that was given. Please notice that they're telling us that 1 over 4 pi e of 0 is this number. So if you'll notice, I actually took out 1 over 4 pi e of 0, took the whole entire thing out and just plugged this in for it. And so we do end up with the limit being equal to positive infinity for part B. So what's the physical meaning of this quantity? Is it physically relevant? Why are you evaluating from the right? So here's what happens. This is about an electric field, right? So the magnitude of the electric field as you approach the particle Q becomes infinite. And we're evaluating from the right because it doesn't make sense for a distance to be negative. So when you're talking about real life stuff, distances aren't negative. We do it in math because we can. Sometimes physics will do weird things with negatives, but typically we're looking at things that are positive when it comes to distance. All right, so that is this video wrapped up. Come back again and we'll do section 2.4.